All right, let's have some fun with vectors. Let's work with vectors. Of course it's going to be fun. I have 4 charges here. Let's make this a 3 microcoulomb, a 2 microcoulomb, a 4 microcoulomb, and a 7 microcoulomb charge. Let's make that one negative and that one negative. And I put a 100 microcoulomb charge there. What is the direction of the force that's acting on that? Well, I need some distances here. Let's make this a square, just why not? We'll make this 2 square root of 2 meters. So 2 square root of 2 meters, 2 radical 2 meters, 2 radical 2 meters. It's going to make life easier in just a second. So now when I'm working this out, well, I have 4 forces here. I'm going to call this 1, 2, 3, and 4, and 5. So the force on 5 is just the sum of the other 4 forces. So F51 plus F52 plus F53 plus F54, and there are vectors involved here. Because I am adding vectors here, I need to worry about direction. I am not adding these together where I'm just doing the calculation and just adding them up like scalars. Direction matters here. I know that this is going to be attracted to charge number 1. So if I look at the forces, I have F51 that is going basically southwest. I have, this is going to be, they are like charges, it'll be repelled. So this is F52. It is going to be attracted there, F53, and it will be repelled here, so F54. These are at a right angle because I have this in the center. If I went through to actually find these distances, this distance will be 2 meters, that'll be 2 meters, and this is the reason why I chose 2 radical 2 for that. So the distance between all of them is between this and any of the outside charges is 2 meters. And so we need to set up a coordinate system. I'm adding vectors here. I need a coordinate system. Now let's go with the straight up traditional like this. I hat, J hat, and then I'll show you a slightly simpler way of doing it. So this force right here, let's just start with F51. It is down and to the left. The magnitude of it, KQ1, Q2 over R squared. So this becomes 9 times 10 to the 9th times Q1 of 3 times 10 to the negative 6th, Q2 100 times 10 to the negative 6th over 4, the 2 squared. Now, notice I did not put the negative sign here. It's because I'm looking at the magnitude. The negative sign is telling me, it's indicating something about the direction, and I know the force is going to be down and to the left. I've already thought through the direction, so I don't need to include the negative sign here. And I get 0.675 newtons down and to the left. I know that's a 45-degree angle there, or 45-degree angle there. So 45 cosine times, it is equilateral triangle. So what I end up with is, this is 0.4773 newtons and 0.4773 newtons. And so this right here is, see, it's to the left, so negative and down. So it's completely opposite of that. So negative 0.4773 newtons I hat minus 0.4773 newtons J hat. Now F2, we're right here. It's going to be very similar to that. Matter of fact, the force should be 2/3 of what that one was. So if we just multiply that by 2/3, or you can go through and plug in the equation 9 times 10 to the 9th, 2 times 10 to the negative 6, 100 times 10 to the negative 6 over 4. So this was the magnitude of F51, the magnitude of F52, and I get 0.45 newtons. Now this is going in that direction right there. We can break it down. This is 0.45 newtons And so 2 square root, this becomes 0.3182. So F52 is to the right, so positive 0.3182 newtons I hat, minus, because it's still down, oh, sorry, it's this one right here. It's up and to the left, so the I is negative and the J is positive, 0.3182 newtons J hat. 5.3 is up and to the right, so they will both be positive, and F4 is, that's going to be positive and that's going to be negative. This one should be twice that because it's twice the charge, and that stays the same. So you can go through and plug it in, but you should end up with the force of 5 from 4 is 0.9 newtons. That's the magnitude. And then when you break it up, so F5.3, making sure I'm doing that up and to the right. All right, so 0.6364 newtons I hat, 0.6364 newtons J hat. And then the last one, it should be basically 3.5 times what that one was, so 0.45 times 3.5. And so F5, that should be a 3 right there. F54, which is down and to the right, 1.575 newtons is the magnitude. And this is 1.1137 newtons I hat, 1.1137 newtons J hat. And so I can add them all up, and I end up with 0.9546 newtons I hat. And then over here, minus 0.6364 J hat. Looking at this, I know it's going to be pushed more in this direction to the lower right than it was being pushed to the upper left. It is going to be pulled more to the upper right than to the lower left. And so what we end up with here is that I would expect it to be pulled in that side to the right more than it is not, and it indeed is. It is pulled down more than it is pulled up. And so if the question was what is the force, we have it right there. We have an I hat and J hat defined right there, so the directions are defined, and we have an answer. Now let's do the same problem, except do it more easily. We already went through the math there. We found the magnitudes. So I set up, I have my 7 microcoulombs there. I have my -4 microcoulombs there. I have my -3 microcoulombs there, and 2 microcoulombs there. And I got my 100 microcoulombs smack dab in the middle. If I change my coordinate system like that, so that's my I hat and J hat. So that basically I've just reoriented my coordinate system. Then what I'm left with now is, so I've got F51, F52, F53, F54. F51 is in the negative J hat direction, so that is negative 0.675 newtons J hat. F52, that's this force right here, is being pushed up in that direction, so in the negative I hat direction, so that's negative 0.45 newtons I hat. F53, so this is my third one, it is being pulled up in that direction, in the positive J direction. So that was 0.9 newtons J hat. And then F54, it's being pushed in the I hat direction, so that is 1.575 newtons I hat. I add them together. And let's see, those are my I hat ones, so I can do that in my head. 1.125 newtons I hat. And then the J hat direction right there, plus, let's see, I'm adding these two together right here. So plus 2 to 5.225 newtons J hat. And this would be the correct answer. This is the force on 5. Now, the answers don't look the same. And again, for those who are rusty on adding vectors here, that's because they're two different coordinate systems. They should have the same magnitude either way. We can find the magnitude of the force on 5. It is not the sum of the magnitudes. It is the magnitude of the sum. And so this would becomes the square root of 1.125 squared plus 0.225 squared, which is 1.1473 newtons. And then in the other coordinate system, if I find the magnitude of the force on 5, that's the square root of 0.9546 squared plus 0.6364 squared. And I should get the exact same thing. I could be off by a rounding error, but 0.9546 squared, 0.6364 squared plus square root, and I get 1.1473 newtons. Hey, I got the same thing. No rounding issues there because I took it out enough decimal places. So sometimes the correct coordinate system, which is one of the reasons why I try to get away from the brainwashing of coordinate systems always like that, because sometimes the math's easier if you do it differently.